If you have any questions, just let me know. Today we'll be dealing mostly with electric potential and problems on electric potential. Okay, I think I can start now. I did say 1:05. Okay, electric potential. Okay. This right here is the formula for calculating electric potential. V, the electric potential, is equal to Coulomb's constant multiplied by the charge that creates the electric potential divided by R, the distance. Now, if we were to look at, say, problem 1, okay, you guys can see on problem 1 there. Let me just make it nice and clear. Okay, this is problem 1 on electric potential. Okay, problem 1. I just want to see if you can see everything I say. Okay, wonderful. Now, if you have any questions, please type them in the chat or just switch on your mic so you can speak to me. Personally, I would like you to speak to me, but if you are afraid, you can just type it and I will regularly check if there are any comments in the chat. Okay, those of you that are actually watching the chat and you see please alert me to those questions in the chat. So let's say question 1. Okay, the question deals with point charges, okay, or the electric potential associated with these point charges. Okay, so they have points A and B are each the same distance r from two unequal charges. Okay, so let's say here is point, this is charge plus q. I'm just trying to draw what is happening here. This is charge plus q and this is charge plus 2q. Okay, so these are our two charges. Okay, and points A and B are each the same distance r from these two charges. Okay, so let's say points A and B are right here and they are the same distance from these two charges. Okay, A, and then we have B as there as well, and the distance is r and they are a distance r away. So 2 points A and B are each the same distance r from two unequal charges. They ask us the work required to move a charge q from point A to point B is, so how much work is required to move a charge q from point A to point B? How much work is required to move a charge? I don't know if I drew that correctly. Might be that I was erroneous or did an error. Okay, but it looks okay. So we start out with what is electric potential. Okay, we've already said it's K Q over R. Okay, that's the electric potential. Okay, now since point A in our drawing, let's say this is point A, and right next to it or superimposed on it is point B. That's A and that's B, and these charges are each the same distance r. Let's make 2q here and we make that distance r, and on this side also a distance r, but this is charge q plus q, so slightly bigger, plus q. So 2 points, same distance from both plus Q and plus 2Q. So we could define the electric potential at point A and we could define the electric potential at point B. So the electric potential at point A, the electric potential at point A, the electric potential at point A is equal to the potential due to charge number 1. So that's K times just Q over R, it's a distance R away, plus the electric potential due to charge number 2Q or charge 2Q. Let me rewrite this. Let me draw this here. We have charge plus Q here. We have A and B. They are on top of each other. I just drew them side by side. And we have charge plus 2Q here. And they are each a distance R away. Distance R away. So the potential, and that's point A, and the potential at B. Okay, so the potential at point A is equal to the potential due to charge plus Q and the potential due to charge plus 2Q. So the potential due to charge plus Q is just K Q over R. That is due to just Q, and then we add the potential due to 2Q. So it is K times 2Q. I should actually write plus 2Q. Say like that, plus 2Q, plus Q. But that just makes it messy. So that's Q, and that's plus 2Q over the same distance, R, okay, from A. Now the potential at point B, we do the exact same thing. It is the potential due to charge Q over R plus the potential due to charge 2Q over R, because they are the same distance away. Now I want to see if it's still in the frame. Now if you add up KQ plus 2Q, what you're left with is 3KQ, 3KQ over R, and there is also 3KQ over R. Okay? So we've now calculated that the potential at point A is equal to 3Q over R, 3KQ over R, and the same is for B. So we've calculated that the potential at point A is equal to 3KQ over R, and the potential at point B is equal to 3KQ over R. But what does the question want from us? Okay, the question asks the work required to move a charge Q from point A to point B is. So to move this charge from point A to point B is, we need that work. Okay, now, how do we calculate the work? The work is equal to Q, the charge, times the change in the electric potential. Okay? Now the change in the electric potential can also be written as the potential at point B minus the potential at point A. Okay? Because we are moving from point A to point B. Okay, so we subtract B from A. B is the end point, the end potential, and A is the initial potential. Okay? So now we have a formula to calculate this energy or this work. So if we substitute our values that we got here, we have that that charge is Q. They told us it is Q. VA we know is 3kQ over R minus, that's VB rather, minus VA is 3kQ over R. That gives us 0, 0 joules. Okay, so to move a charge, is the question? Yeah. The work required to move a charge from point A to point B is 0 joules. Okay, because like I drew earlier on, there is one type of drawing that explains it. Those two would be superimposed. I just drew them next to each other, A and B, but in actual fact, they are right on top of each other because they are the same distance away. So they are right on top of each other in that scenario, meaning to move from point A to point B requires no energy, you are already there. Everyone with me on that question? Okay? Everyone with me? Thumbs up if you understood that question. We have one person. Two, thank you. All we have to do is just calculate the work. Okay, first we calculated what the potential at those 2 points are, and then we just had to calculate the work required to bring in charge number 3. Thank you, everyone. Question number 2. Let's look at what question number 2 asks. Several charges in the neighborhood of point P produce an electric potential of 6 kilovolts relative to 0, which is at infinity, and an electric field of 36 in the I-hat direction at point P. So we know that these charges uh, near point P create an electric potential of, this electric potential is 6 kilovolts at point P, at P, and there is an electric field in the I-hat direction, or not just say let's just say there's an electric field that is 36 newtons per coulomb in the I-hat direction. This is at point P as well. They want us to determine the work required of an external agent to move a 3 microcoulomb charge along the x-axis from infinity to point P without any net change in the kinetic energy of the particle. Okay? So if there is no net change, it means that the total work that they are going to do to bring in this charge must equal the change in the kinetic energy. Okay, that is the work energy theorem. Now the total work is done by the external work plus the electrical work. And that should be equal to, there is no net change in kinetic energy, and so that is equal to 0 joules. Therefore, the external work is equal to the negative of the electrical work. Just basic algebra. So the external work is equal to the electrical work. So we have that the external work is equal to the negative of the electrical work. Now, what do we know about the electrical work, or rather the external work? We also know that the external work done, you need to know all of these formulas, is equal to the change in the potential energy. And what is the change in potential energy from your formula? Is Q delta V. We've just dealt with this formula. Now, if I plug in the charges, Q is equal to, what do they tell us the charge? That it is 3 microcoulomb. 3 times 10 to the negative 6 coulomb times the change in the potential. The electric potential is 6000 volts minus 0 volts at infinity. Let me see if that is in, minus 0 volts at infinity. That gives us the external work of 0.018 joules, or you can write it as 18 millijoules. So 18 millijoules of work required to bring in a charge, an external agent, to move a 3 microcoulomb along the x-axis from infinity to point P. So this is the amount of work required to bring in this 3 microcoulomb charge. If you don't understand, just raise your hand and tell me where it is that you are struggling with. Otherwise, I will continue. These are all basic type problems. Let me just continue with question number 3. This has to do with the electric potential at 2 points in space. And just some advice, you guys need to know how to differentiate between electric potential and electric field, because it only gets more integrated from this point on. Okay? So the electric potential at 2 points in space is V1 is equal to 200 volts, so 200 volts, and V2 is equal to 300 volts. Which of the following statements is true for moving a point charge Q from point 1 to point 2? Okay, so we're moving from point 1 to point 2. Which of those statements are true? The first statement, statement A, says the work done by an external agent to move Q from point 1 to 2 is positive. The work done to move from point 1 to 2 is positive. Let's just look at statement number A. Let's look at statement A. Okay, to calculate the work done, the external work, it's equal to Q delta V. Okay, and if we work out Q, we don't care what the charge is, but let's calculate. We have the two voltages, 300 volts. It's from 1 to 2, so it is 300 volts minus 200 volts. That will give us positive Q times 100 volts. Okay, it's still positive here, still positive. Now this is only positive if Q is bigger than 0, or Q itself is also positive. Okay, that is statement 1. Statement 1 is only true if Q is bigger than 0. Let's look at statement B. We can't determine the work done because we don't know the direction of V at the 2 points. That is false because electric potential is a scalar, not a vector, so we don't need the direction to calculate it. False because V equals a scalar, not a vector. So we don't need the direction. Let's look at C. Is C true or false? The first one, A, is true only if Q is bigger than 0. It is only true if Q is bigger than 0. B is false. C is the work done by the electric force exerted on Q, or work exerted on Q in moving it from point 1 to 2 is, from point 1 to 2 is negative Q 100V. Now the work electric, we know work electric is equal to the negative of the electric potential, or the, let me write it this way, it's equal to the negative Q delta V. Remember, this is the electric work now. It's negative Q because it must be equal to Wxt. That's why it is negative. So Q is negative Q 300 volts minus 200 volts. That's equal to negative Q 100 volts. Okay, so that is the electric work. The work done by the electric force will always be negative Q 100 volts. Now we answer the question. So this is true. C is true. Now C is, A and C can't be true because A is only true if Q is bigger than 0. There are conditions to it being true. Only A, it can't be only A that is true. Only C is true, yes. A and B can't be, B is false, B is false. So let's check. We can actually check. I forgot to check for the previous one, but let's check for this one. The answer is only C is true. Question number 4. If there are no questions, I'm going to continue. Question number 4. Point A at 2.3 meters at point, so let me just rather draw it. At 2 on the x-axis and 3 on the y-axis, that's point A. Then we have point B at 5 on the x-axis and 7. This is 3, this is 7, not to scale. So those are the 2 points. Are in a region where the electric field is uniform and given by 4I hat plus 3J hat. There is an electric field there, and that electric field is equal to 4I hat plus 3J hat. That's the electric field. What's the potential difference between A and B? So we want VB minus VA. Okay, that's the potential difference. That is what we want. So first we need to calculate exactly what is the potential there. what is VA, and then we need to calculate what is VB. Then we can calculate VB minus VA. So how do we work out VA? So let's first work out the potential at point. The electric field, let me write it here, is equal to 4I hat plus 3J hat. That's the electric field. Now let's work out the potential at point A, VA. How do we calculate the potential at point A? Or instead of doing it like that, let's calculate the distance between those 2 points, and then we calculate what the electric field is. Okay, using a displacement vector instead of reference to 0. So we have the position vectors. Okay, they've been given to us. Now the change in their position vectors, let's just say the change in R, or rather this is just the distance between A and B. Okay, the distance between A and B will just be 5 minus 2 in the I hat direction. Okay, 5 minus 2 in the I hat direction plus, then it's 7 minus 3 in the J hat direction. This is the position vector. That gives us 3 in the I hat direction plus 4 J hat direction. Okay. So 3 plus 4, this is the delta R vector. That is the vector between these two, A and B, between those 2 points A and B. Now if we calculate the potential difference, how do we calculate the potential difference if we have the distance between them? We know VB minus VA is equal to the electric field, this is a formula in your textbook, dotted with the position between them, or the distance between them. Okay, and we already know that the electric field is equal to, don't forget that negative, the electric field is equal to 4I hat plus 3J hat, and we just worked out that this position between, or the distance between these two vectors is 3I hat, that's 3J hat, 3I hat plus 4J hat. If you are getting lost here, you need to go and review some of your work. The negative stays outside. Let's just do this dot product quickly. It's 4 multiplied by 3 plus 3 multiplied by 4 let me just check if there are no questions. None yet. So there we have that. That's the dot product, you should have learned this in first semester. So it's negative 12 plus 12. The answer is negative 24 volts. That is the potential difference between those 2 points, negative 24 volts. Now, of course, you could have calculated the potential for point B first, and then the potential for point A, but this is the easier method. If you can just find the displacement vector between the 2 points, you can just find the dot product, the negative of the dot product between the electric field and the displacement vector. So let's just check if it's 24 volts actually. Make sure that that is the correct answer. 24 volts. Let's check. Yes, that is correct. Of course, the voltage here is a scalar, so 24 volts. 24 volts. That is just for the electric field. Correct answer, 24 volts. Now, question number 5. A particle with a charge of 2 millicoulomb, please don't confuse that with micro, moving in a region where only electric forces act on it, has a kinetic energy of 5 joules at a point A. The particle subsequently passes through point B, which has an electric potential of 1.5 kilovolts relative to point A. Determine the kinetic energy of the particle as it moves through point B. Okay, so we know that electric potential energy is equal to Q delta V. Okay? So we are calculating the electric potential energy. This is 2 millicoulomb multiplied by the change in the voltage, which is 1.5 kilovolts, so 1500 volts relative to point A. So that is the potential difference between these two. So the electric potential is, or the potential energy rather, is 3 joules. So this is the potential energy for this particle moving from point A to point B. Now, if we apply the law of energy conservation, we know that the change in the kinetic energy plus the change in the potential energy should be equal to 0. That is the conservation of potential of energy. Now, therefore, delta K plus 3 joules should be equal to 0. Therefore, delta K, the kinetic energy is equal to negative 3 joules. So the kinetic energy is negative 3 joules. The change in the kinetic energy is negative 3 joules. Now, the change in the kinetic energy is the kinetic energy at point B minus the kinetic energy at point A. That's equal to negative 3 joules. The kinetic energy at point B would then be equal to kinetic energy at A minus 3 joules. Remember, this is what we want. Okay, we want the kinetic energy of the particle at point B. What is the kinetic energy of the particle at point A? They already gave it up to us. It is 5 joules. It's 5 minus 3 joules. So the kinetic energy at point B is 2 joules. 2 joules is the kinetic energy at point B. 2 joules. I see there are no questions. So I'll continue. Question 6. If you have any problems, just raise your hand and you ask the question where you are stuck, and I will continue. These questions are elementary so far, basic. And they will progressively get more difficult as we go on. Okay, I will only be finishing a question for 10 questions today, but they do get very difficult as we go on. Not difficult, they get more involved. These are the basic type ones. Okay, just to whet your appetite. So, question is, particle A, it has a mass m and a charge q, and particle B, which has a mass m and a charge 5q, are released from rest with a distance between them equal to 1 meter. Okay. If q is equal to 12 microcoulombs, what is the kinetic energy of particle B at the instant when the particles are 3 meters apart. Okay, so what is the kinetic energy of part B when they are 3 meters apart? Now, since both particles start from rest, we have that the momentum originally is zero, right? And since they don't say anything about external forces, uh, we assume that the momentum must stay zero at all times. The law of conservation of momentum. Okay, it's the law of conservation of momentum. Therefore, the mass times that since they gave us the mass as m, you should have that would give you a hint on what formulas or what laws to use. The momentum at point A is the change in the momentum at point A is zero from it because it's at rest. Its initial momentum is zero because it's at rest. Now we know that the mass of A is equal to the mass of B, which is equal to just m. They tell us there they both have a mass of m. Now if we plug that in there, mVa plus mVb equal to 0. If we divide throughout by m, we get Va plus Vb is equal to 0. Therefore, Va, the velocity of A, is equal to the negative of the velocity of B. So now we know what each one's velocity is as well in relation to the other. Since their velocities have equal magnitudes, their kinetic energy must also be equal. Okay, because they have the same velocity, and kinetic energy is equal to a half mv squared. So we can say that the kinetic energy of A is equal to the kinetic energy of B because their velocities are the same and their masses are the same, which is equal to a half mvb. Okay, and we can just write B there. We don't actually need to write VB. We can just write V. Now the total kinetic energy is the sum of the kinetic energy. So kinetic energy of A plus the kinetic energy of B. But since the kinetic energy of A is equal to the kinetic energy of B, we can just write it as 2 times the kinetic energy of B. Now, what is 2 times the kinetic energy of B? We've already written down the kinetic energy of B. That is just mvb squared. Okay? So the total kinetic energy is equal to mvb squared. That is the total kinetic energy. Now we need to calculate the potential energy. So we know so far the total kinetic energy is equal to mvb squared. That's the total kinetic energy. Now if we calculate the total potential energy when they are 1 meter apart, okay, so the initial potential energy when they are a meter apart is just K times Q A QB over the initial distance R. That's the initial distance of 1 meter. That's K. Initial QA is equal to just QB is equal to 5Q, and that's the initial distance. And if you multiply it out up there, it looks at 5kq over r initially. So that's the initial potential energy. If we substitute in all the constants and so on, we get 5 times 9, I don't use 8,99, it's 9 times 10 to the 9 multiplied by 5, that's already 5 is already there. The charge they tell us is 12 microcoulomb, so that's 12 microcoulomb over initial distance is 1 meter. That gives us an answer of 6.473 joules. Okay, so 6.43 joules is the initial potential energy. Okay, now what is the final potential energy? That is the initial potential energy when they are 1 meter apart. Now how do we calculate the final potential energy? The same method. So the final potential energy we will calculate using the same method. It will be K QA QB over R final over R final. But we know that that all will equal to 5K cube because we've already done this problem. Oh, I forgot to square it on the other side. It's KQ plus that I should have put in the square there. Just remember not to forget the square. R final. If we substitute in everything, that's 9 times 10 to the 9. That is 12 microcoulomb. 10 to the 6. And we should square that. I forgot to square it previous calculation. My calculation is still correct. I just forgot to write the square sign there. And they are now how far apart? 3 meters apart. And if you work that out, it is 2.158 joules. This is what I got. And important, does this answer make sense? Okay, if they are further apart, is the electric potential, is the potential energy lower? Yes. Okay, so that is why this one is 2 and the other one was 6. The electric potential energy is linearly decreasing. So now we have the initial potential energy and the final potential energy. We know that the total kinetic energy should be equal to the total kinetic energy should be equal to the initial potential energy minus the final potential energy. That should be the total kinetic energy. Okay, because that's the change. No energy is being lost. All that potential energy that is lost is converted to kinetic energy, which is what we want. But we've already established that this initial potential energy is 6.473 joules minus the final potential energy is 2,158 joules, and that gives us an answer of 4.315 joules. Okay, so we have the kinetic energy, okay, as this particle is moving, or rather the initial potential energy when it was 1 meter apart, and then we also have the initial potential, the final potential when it's 3 meters apart. We calculated those, and we know that none of the energy is being lost, so all of that energy must be converted to kinetic energy. But we've already found a formula for the total kinetic energy, remember? We have found that the total kinetic energy is equal to 2 times the kinetic energy of B. And what do we want? The kinetic energy of point B. So the kinetic energy of point B therefore is equal to the total kinetic energy, which we just calculated, divided by 2. So it will be 4,315 divided by 2. That will give you the kinetic energy at point B. And that answer is equal to 2,16 joules. So the kinetic energy at point B, due to the change in the potential energy, is equal to 2.16 joules. Okay, that is a neat little calculation. Oh yes, there, Asabongwa, it should be 5kq squared. I just forgot to put the square there. Now we go to question number 7. See, no questions, so I assume this is pretty elementary for you guys. What was the answer there? 2.16, so basically 2.2. Let's check. Yes. Question 7. A uniform electric field of magnitude 325 volts per meter is directed in the negative y direction in the figure. The coordinates of point A are negative zero point 0.2, negative zero point 0.3 m, and those of point B are zero point 0.4 and zero point 0.5 m. What is the electric potential difference VB minus A using the dash line? So if it uses this path, if you move along this path, what would be your electric potential difference? How do we work that out? We know that VB minus VA is equal to, and we use the formula we used earlier, the negative of the electric field dotted with the delta R, the position vector between these two. Okay? We can also write that position vector as equal to the position at point B minus the position at point A. That displacement vector between the two. Let's first calculate that displacement vector there. Let's calculate that one first. Let's first calculate that displacement vector, delta R. The displacement vector is just RB minus RA. So it will be 0.4 minus 0.2, that's the x direction, and the I hat x direction, plus for the y hat direction, or the j hat direction, sorry, we have, let me just see, is there a question? None. The y hat direction, we have from point B to point A, we have 0.5 minus minus 0.3. In the j hat direction, if we work that out, that is just elementary. 0.4 plus 0.2, that is 0.6. In the I hat direction, I keep wanting to make a j. In the I hat direction, plus, that is 0.5, that's 0.5, plus 0.3, that's 0.8, in the j hat direction, and that's in meters. So now we have this displacement vector here. Okay, it's 0.6 I hat plus 0.8 in the j hat direction. Now we only need the electric field, which they've actually given to us. Okay, so we can actually do the whole sum. VB minus VA, that potential difference, is equal to negative of the electric field. Can you still remember what the electric field is? Let's just go back and then show you what that value was. That electric field had a value of 325 in the negative y direction. So in the x direction, this electric field was 0. It has no x component. But in the y direction, it was in the negative y direction at 325. This is just basic vector components. There's your electric field. We should dot that with the displacement vector of 0.6 in the I hat direction. plus zero point 0.8 in a j hat direction. If you do the dot product, you will get out negative. Just make sure that that's zero point 0.6, yes, that's 0. Okay, let me just do it at 0 dotted with 0 0.6. So obviously that will be 0 plus we have negative 325 dotted with zero point 0.8. That leaves us with this falls away to 0. So it's negative 325 times zero point 0.8. So 0.8, 80% of that of 325 is 260. There's still a negative there, so it's negative 260. There's still a negative up in front. Negative 260, which leads us finally to positive 260 volts. So the potential difference between A and B, if you take that path, remember this is path dependent. So that will be 260 positive. Just make sure of your signs, okay, that you don't switch them up. In this case, if you did not have the negative outside the formula, you would have gotten a negative value. Question number 8. A particle with mass, that is a normal, that is a proton, I believe, or is it an electron? Charge 3.2 times 10 to the negative 12 coulomb, moves along the positive x-axis with a speed of 4.8 times 10 to the 5 meters per second. It enters a region of uniform electric field parallel to its motion and comes to rest after moving 2 meters into this field. What is the magnitude of the electric field? So now they're trying to get you to calculate the magnitude of this electric field. And what you should know is that the work done by this particle is equal to the change in the kinetic energy. That's the kinetic energy. The work kinetic energy theorem. The work energy theorem. That means it's the change in kinetic energy is the kinetic energy final minus the kinetic energy initial. Now, since the particle comes to rest after moving that distance, the final kinetic energy, Kf, is equal to 0 since it comes to rest. Okay? Now, the work done by the electric field over a dead distance d, the work done because the electric field itself is doing work, opposes this motion. Okay, so the work done by the electric field opposes this motion. So the work done by the electric field, that's force times distance, it's forces in the opposite direction, is equal to 0. Equal to 0 minus a half mv squared. Okay, that's the kinetic energy, the work energy theorem. We want the electric field. Now the electrostatic force, we know that electrostatic force is equal to charge, force, electrostatic force, or electric force, you should have dealt it from the last thing, is equal to Fe. This Fe here is equal to Q times the electric field, and then we still multiply by the distance. Electric force is QE. And that negative that was there is still there, and this is a half mv squared. And this is the initial velocity because the final kinetic energy is 0. So if we want the electric field, it is therefore equal to a half mv V initial squared over the charge divided by the distance. Let me rewrite it. Electric field, I can write it as such as well. M V initial squared 2 QD. And if we plug in everything that we have, the mass is 6,7 times 10 to the negative 27 multiplied by the velocity initially 4,8 times 10 to the 5 meters per second, 2 times the charge. It gave us a charge that's 3.2 times 10 to the negative 19. And how far does it travel into this electric field? Just 2 meters. And if you work all of that out, plug it in your calculator, you work it out, you should get an answer of 1206 newtons per coulomb is this electric field in this particular direction. Because remember, electric field is a vector. So there we have 1200 as the electric field, 1.2 kilonewtons per coulomb. Let's check. Yes, that is correct. That is indeed the correct uh, volume, or rather not a volume, the correct electric field that we calculated. Now our second to last question. Question number 9. If A is equal to 30 centimeters, B is equal to 20 centimeters, Q is 2 nanocoulomb and big Q is negative 3 nanocoulomb in the figure, what is the potential difference VA minus VB? Okay. Let's first work out VA. Let's first work out VA from that situation. Let me just give you all the information. Let's work out VA. That is just equal to K. VA is equal to the first charge. The potential at point A is equal to the first charge, which is the distance A away. So it is KQ, K small q, and it's a distance A away, plus KQ. The second one is due to point big Q. So this is due to big Q. The potential is due to big Q. And it is a distance of A plus B away. A plus B. Now if you plug in everything we know, we can actually solve for it. A is 30 centimeters, so it's 0.3. We have that this is 9. K is 9 times 10 to the 9. We can actually take it outside, but I just want to show you. The charge Q, small q, is 2 nanocoulomb, 2 times 10 to the negative 9. Same thing here, 9 times 10 to the 9. And then the charge is negative. It's negative 3 nanocoulomb. Negative 3 times 10 to the 9. And then A plus B, that is 0.3. A plus B is 30 plus 20, that's 50. So that's 0.5 meters. So the potential at point A due to those two charges is equal to, this is a very simple type problem, is equal to 6 volts. Essentially, that is positive 6 volts. So the potential due to A is positive 6 volts. Okay. Now let's calculate the same operating principle. So the potential due to point A is equal to 6 volts. We do the exact thing for point B. Two charges are creating potentials at point B. It is the small q charge and the big Q. So for the small q, it is the small q, and it is the distance of A plus B away from point B, plus big Q is a distance of just A away. And if we add all of this again, it's 9 times 10 to the 9. Small q is 2 nanocoulomb. A plus B is zero point 0.5 plus 9 times 10 to the 9. And then q is equal to, big Q, remember, is negative 3 still, negative 3 nanocoulomb. And then we have only A here. Look how it has switched. Only A here, which is zero point 0.3 meters. And if we work it out, you plug that into your calculator, you should get negative 54 volts. So A is 6 volts, B is negative 54 volts. Okay, therefore, we want to calculate VA my B. The potential difference between A and B is equal to 6 volts minus 54 volts is equal to 60 volts, positive 60 volts. So the answer is positive 60 volts. Let's check. And yes, that is indeed correct. There is a positive 60 volt potential difference between A and B. Question 10 is the easiest. There is no calculations. So we end on a high note. An electric field is created by a positive charge. Okay, so there's the positive charge. The distribution of the electric field lines and equipotential lines is presented on the diagram. So these are equipotential lines. Concentric about it. Which statement about the electric potential is true? Okay. Before we even look at the statement, let's calculate the electric potential. Okay. Which one has the biggest, or let's say the biggest electric potential? The one, let's calculate, how do we calculate the electric potential? It's KQ over R. Okay. So the one with the biggest electric potential would be the one closest to the sample, or closest to the charge. Now, A and D is the same distance away, so the electric potential will be exactly the same. And this electric potential from A and B would be bigger than the electric potential for B, which would be bigger than the electric potential for C and E, which is the same distance away, so their electric potential will be exactly the same. So this is what we've just by looking at the drawing and using the formula. So we should have that A and D should be equal, and then C and E should be equal, and B in the middle. It's A. So let's check A. Yes, that is correct. Okay. Now that is all that we have time for today. Thank you for listening. I will see you next week. And if you have any more questions, you can just ask our next demi that is going to be tomorrow. That would be Arnold. Okay. All the best. Thank you for listening.